Today I'm going to tell you about the Lightning Memory Map database. I think you're going to agree by the end of the presentation that the name Lightning was well chosen. So my name is Howard Chu. I am a founder and currently the CTO of a company called Symas Corporation. And I've been working with OpenLDAP since 1999. I became the chief architect of the project in 2007. I've actually been working with open source software since before there was such a phrase as open source software. I worked on all of the GNU tools back in the early 1980s. I invented Parallel Make. Any of you guys who are using Parallel Make, that's my code. All right, so just an overview of what we're going to cover. I'll give you some background into how we designed the Lightning database, so to why it's behaving the way it does. Some of the features that the database provides. It's a transactional database. I'll give you a look at the overview of the API so you can actually see some live code and see how the code is done. And then I'll talk a little bit about how it works on the inside and some special features we've added to it. And then finally I'll give you some benchmark results and some other information that we've compiled. So first of all, the API is inspired by BerkeleyDB. How many of you have used BerkeleyDB? All right, fair number. You know, OpenLDAP has been using BerkeleyDB continuously since 1999. It's been our #1 primary database. We've spent a lot of time inside the code of Berkeley as well as using it, so we're very well familiar with it. We found through many years of experimentation that there's a lot of features in BerkeleyDB that we've never had a good use for. So in the Lightning database, we've stripped all of those things out. There's also a lot of issues that you run into when you're deploying BerkeleyDB. Things that administrators have problems with, and we've omitted all of those. So, it's a very simple database. It's a key value store. It uses a B+tree. It's fully transactional, fully ACID compliant. Our locking system uses MVCC, so readers never block, ever. We use a memory mapped file and no other cache of any kind, so it just uses the OS file system cache. It's completely crash proof. It never overwrites any live data, so nothing can ever get corrupted by an interrupted write. It's very, very compact. The source code is under 6K lines of C code. The object code is, if you compile with GCC-OS, compile for space optimization, it'll be under 32 kilobytes. And it runs on pretty much anything that supports virtual memory and memory mapping. Concurrency allows both multiple processes and multiple threads to concurrently use the database. It's a single writer model, but multiple readers. So writers don't block readers, readers don't block writers. And because there's no locking on reads, the reads scale perfectly linearly across as many CPUs as you can throw at it. Because there's only single writer, there's never any deadlocks. This is one of the things we always ran into with BerkeleyDB is you were running into deadlocks all the time. Just as a normal course of operation, you had 50 writers going at once, you were always hitting deadlocks. So the database appears fully isolated. Any transaction looks like it has a complete snapshot of the database all to its own. So it's fully isolated with multi-version. We also support nested transactions, and we support batched writes, which is just another way of saying multiple writes in one transaction. So the general scheme is we never overwrite any live data. And because of this, the database structure can never be interrupted in the middle of a change. So we can't do any corruption into the data structure itself. We don't use any write-ahead transaction logs. We don't do any log cleanup. There's no maintenance. There's no compaction. and there's no recovery after a system crash. You just power it up and it works. Since we return data directly from the memory map, we can actually give you read access to the data without doing any mallocs, no memcopies, no nothing. You just get directly to the data. Likewise, we can do the same on writes. In the default case, we don't handle writes that way. In the default case, we run the memory map as a read-only map. And that way, if you actually have, if you're developing code and you still have bugs in your code, and you accidentally dereference a pointer into the memory map, you'll get a seg fault. You'll get an instant crash, and you'll know you've got a bug that you need to fix. Since we use the OS cache, there's no wasted memory anywhere. With BerkeleyDB, when we were using BerkeleyDB, you had data present in the file system cache, you had it in the Berkeley database environment cache, and then we had another copy of it in the OpenLDAP slapd cache. So all of that's gone. We support storing memory maps and the database at a fixed memory address, assuming that the OS supports it. So if you take advantage of that feature, you can actually store pointer-based objects into the database and then use them directly out of the memory map. You could execute code directly out of the memory map if you wanted to. So the API is kind of a simplified copy of the BerkeleyDB API. Just to give you an example, we ported the OpenLDAP back BDB code to use MDB. It took about 2 days, and most of that was just doing global search replace. So the library is written in C, but we have third parties have already written wrappers for it in other languages. We will probably do a Java wrapper for it fairly soon. Everything in this database is transactional, so there is no simplified API that doesn't use transactions. Everything is wrapped in a transaction. When you get data back from the database, when you do a read operation, you're seeing data that lives directly in the memory map. So the data is owned by the database and never needs to be cleaned up by the application. We tried to keep a pretty rational naming scheme for the function names. So here's an example of a little C program that uses the LMDB API. Here's the exact same program using the Berkeley API. And I'll show you them side by side so you can get an idea of what's changed. In BerkeleyDB, if you want to use transactions, you have to initialize a whole half dozen other subsystems. You've got to initialize the memory cache, you've got to initialize the transaction system, the locking system, the logging system, all of this stuff. And with the Lightning database, it's just all there by default because everything is transactional by default. When you actually pass data values in and out of the library, with BerkeleyDB, they use a fairly complex data structure for passing values in and out. And you always have to initialize the entire structure to all zeros before you use it, because otherwise very bizarre things will happen. With Lightning database, structure is just a value pointer and a length, and that's all it is. Just use it directly. Here you see a little bit more of the complex initialization. In that case, on the Berkeley side, you have to tell it, I'm using my own memory that I've provided to you, so don't malloc it for me. And again, with Lightning database, you don't have to worry about details like that. So the data structures are simpler. The setup of an application is simpler. And the setup of a database is completely reliable. In BerkeleyDB, you actually it stores each database in a separate file. So if you have errors in the file system that might prevent your files from being created, that'll impact the Berkeley transaction system, but it won't be able to recover because it can't roll back a failed file system operation. So again, just Lightning database is a lot simpler. Here's an example of configuring these databases in OpenLDAP. You can see, first of all, you have to tell slapd what kind of database you're using. Then you've got to tell it the directory path you're going to store it. And then after that, you've got to tell it the tuning. For Lightning database, all we tell it is the maximum size of memory we want it to use. So here I've used 4 gigabytes. With Berkeley DB, there's slapd caches, there's Berkeley caches, there's the transaction logs and the log buffers that you're going to use. Then you have to tell it the maximum number of locks and lock objects you might encounter, and then maximum locker IDs. It gets fairly complicated in a large deployment. Okay. So how do things work on the inside? It's basically inspired by an append-only Btrees. And the code for that came from FreeBSD, but it was heavily modified. So if you have an append-only Btree, that means you never, ever overwrite data. So every time you write a record, you're always using new disk space. Anytime you want to modify an existing page, what you do is you make a copy of it, and then you modify the copy. This structure is inherently multi-version. Every transaction that you ever perform on the database still exists in the file somewhere. And you can find it by finding the root node of that transaction. So for example, with a very simple tree, if I'm going to do one write operation on it, I'll create a new leaf node, and then I have to create a new root node that points to it. So now my tree actually has 2 versions. It has 2 root nodes. They both point to valid versions of the tree. And if I was to continue modifying it, I would just, again, make a new copy of the leaf node, create a new root node, and so on. So you see that updates are always performed from the leaf node upward towards the root. When you do these modifications, you actually have to make a copy of every intermediate page between the leaf and the root. Anything that's not on the path of the modification can be left untouched. And the root node is always written last. This kind of approach has a couple of advantages. Even though you're doing a lot of I/O because you're making complete copies of so many pages, the I/O is relatively fast because you're always writing in a linear sequence. You're always appending linearly to the end of the file. In case of a system crash, it's fairly easy to find your last valid state. You can just seek backward from the ends of the file until you see a valid root node. Unfortunately, this approach is extremely inefficient for disk usage. First of all, the disk space just grows without bounds. Nothing is going to stop it from growing. And you'll find that after only a few transactions, 99% of your space is for old data that nobody cares about anymore. Databases that are deployed with this approach, like MongoDB, they just have to throttle writes while they do a compaction phase. So with Lightning database, it's still copy on write, but we only have 2 root nodes. So we ping pong between them like a shadow buffer. Fast startup is a simple advantage there. And we only have 2 versions of the data. So now I've added a transaction ID stamp to the root nodes. And again, I'm doing the same operations as before. Now the highest numbered root node is the one that's valid. Also, you see as changes progress, old pages can actually be reclaimed. You can tell when you're performing these updates that this data page is no longer being pointed to by anybody. And here the yellow leaf node can be reclaimed. So that was a very simplified view of things. In reality, we actually maintain two sets of Btrees in the database. One of them stores the user data, which works the way it was just shown. The other one stores lists of the page IDs that have been freed. So this is how we track our free space. And because we're tracking the free space this way, we don't ever need a garbage collection pass. So again, there's two root nodes to begin with. They each contain two root pointers, one for the free list and one for the data list, or data tree. And at the start, they're all empty. So we write our first data page, and we record that we're pointing to it in one of the root nodes. Then we write a new data page and a new free list page. Then we update the root node and say, look, here's our data root, and now we have a free list root. And this goes on with subsequent pages. So there is a caveat. If you hold a read transaction open for very long, it will prevent free pages from being reused. And then in that case, all subsequent writes will act like pure append mode. So you generally don't want to do that. Keep read transactions open as short as possible. Right, so the library supports a single writer. There's a single mutex that serializes every write transaction. And this mutex is shared multiprocess. So this allows us to do multiprocess concurrency. Now, even though the readers are lockless and they never block, we still track the existence of read transactions. And this allows us to know when pages are no longer being used. So any transaction starts by taking a snapshot of the current root page. Once the snapshot is taken in memory, it has a complete snapshot of the database that it can do whatever it wants to, and no subsequent changes will affect that snapshot. The currently valid meta page, as I showed you before, it's just whichever one has the highest transaction ID at the time. During a commit, we actually perform two flushes. One, we flush all of the data pages, and then once that's completed, then we write a new meta page and perform a sync on that. So if the system crashes before the meta page is synced, then that particular transaction will be lost, but the rest of the database remains intact. So there's a reader table that keeps track of which read transactions are open and which version of the database they're looking at. So anything that has a live version, that means none of its pages are available for reclaiming. All of these table slots are stored in thread local storage, so again, we don't need locks to access this information. Likewise, the writer doesn't need to acquire locks to examine the reader information. We don't care if the writer sees out-of-date information. All we care about is that we find the oldest outstanding read transaction. Once we find the oldest one, we avoid it. Okay, so there's a few special features about the database that make it more useful than a vanilla key value store. We support doing key comparisons in reverse byte order. We also support native binary integer keys. Most of the key value stores just treat the keys as strings and do essentially memcomp on them. If you know that all of your keys are going to be integer, we can actually compare them 2 or 4 bytes at a time, so key comparisons are much faster. also with Berkeley DB, we found you very often wanted to use a custom key compare function, but if you did, you risk corrupting the database because the standard Berkeley tools like dbdump and dbload didn't know what your custom function was. So even though you could take a backup of your database using dbdump, if you had to reload it using dbload, it would load in the wrong order, and then your application wouldn't work. So we've tried to completely minimize the use of custom compare functions. We still support them, but in most of the cases you won't need to use one. We have a special append mode for bulk loading a database when you know all of your data is already in sorted order. Then in that case, the bulk load basically runs as a streaming write. It just performs sequential writes all the way through. There's also a reserve mode, which is useful if you're generating output objects that are fairly complex and you want to generate them on the fly. You can just ask the database for a buffer of the appropriate size, and it'll give it back to you, and then you can generate your output object directly into the write buffer. So again, we're just avoiding memcopies. As I mentioned before, you can store the database at a fixed memory address, and then every application that connects to the database will see all of your objects with the same address. We also support multiple namespaces within a single environment. This is a feature that OpenLDAP uses to store all of the attribute indices for all of its main entries. It's also what SQLite uses for index tables. We also support multiple data values for a single key, or duplicate values, duplicate keys. Berkeley DB supports this in two different ways. They support multiple values in random order and also multiple values in sorted order, and we only do this with sorted order. And again, when you know that all of your data values are of a constant size, you can set a special flag on that, in which case the database will store them all in contiguous memory. And so you won't pay any overhead. Normally it's 8 bytes per key. So if you know that they're all fixed size, then that 8-byte overhead disappears. You can perform a hot backup of the database. It doesn't matter what activity is happening on it. The backup routine just opens a read transaction, which gives it a complete snapshot of the database, and then it essentially does one write system call. On Linux, it actually has to do multiple writes. You can only write 2 gigabytes at a time. But again, this runs at the maximum speed of your storage hardware. So since the time that we introduced Lightning Database, which was first presented at LDAPCon in autumn of 2011, we've been pushing it into various other open source projects. The code for CF Engine hasn't yet been adopted upstream. It's sitting in GitHub right now. And we have some other NoSQL and SQL targets that we'll be porting to in the near future. We've already demonstrated pretty good performance gains in OpenLDAP using this database, and also some speed tests in SQLite. I was a little disappointed because, the emphasis of this database is fast read performance, and what I found with SQLite is read performance didn't change by very much. It changed by like 0.1%, simply because most of your processing time in an SQLite read is just in parsing the SQL statements and generating an optimized query, whatever they call that is. In Memcache D, so Memcache DB is a version of Memcache D that was adapted to use Berkeley DB as its data store. So I took out the Berkeley code and replaced it with Lightning DB. And you find that the IOs are much faster. And in fact, our read operations are faster than the original pure memory Memcache D. Now, this is only true in the multi-thread case. In the single-thread case, we're about the same speed. In the multi-thread case, what you find is Memcache D uses locks on read accesses, and Lightning DB doesn't. So I'm going to give you a sample of some of the benchmark results, but if you're curious, you can get all of the complete reports on our website. First of all, this micro benchmark, this is based on the benchmark that Google published for LevelDB. All of the test configurations in this benchmark came originally from Google's test configurations. Except I went a few steps further. With the original LevelDB report, I think they used one hard drive and one file system. I was a little curious, so I tried out every file system that I could load on my machine. First of all, a lot of these guys, they claim that their database is lightweight, and they claim that it's very fast. You'll see that the top value there, DB bench, that's Google's LevelDB. And in the middle there is MDB, Lightning Database. You can see that our process size is smaller by at least a factor of 4. And everybody else is much larger. Berkeley DB is huge. Here's a test performing sequential and random reads of small records. So these are 16-byte keys and 100-byte data values. On the left side, it's sequential reads. On the right side, random reads. That's reads per second. Yeah, I think most of the results speak for themselves. Here's using 100,000-byte records. In the abstract for this presentation, I said Lightning Database is multiple orders of magnitude faster than everything else out there. I mean, this is what I'm talking about. Here's the same data presented on a log scale chart, just so you can see that those guys aren't delivering zeros. They actually are returning data. It's just so much slower. This is asynchronous write performance with the large records, 100,000-byte records. This is batched write, so this is multiple write operations in a single transaction. This is synchronous write performance, so we're actually performing an fsync after every transaction commit. One of the interesting things you see here that the original Google results don't show you. In the original Google test, they ran this particular test configuration only 1,000 iterations. On these results, I've run it for 10,000 iterations. And the interesting thing is that the LevelDB speed drops by a factor of 10 from its original value. So they're doing something strange that is interfering when you get to multiple records, multiple operations. This is a new slide. I just added this yesterday because somebody at Google emailed me 2 days ago complaining that my tests were not showing the strength of LevelDB. He said that I was deliberately configuring these tests to show LevelDB in a poor light, even though I'm using exactly the configuration that the LevelDB authors used themselves. So anyway, he said, what happens if you create a test that plays to LevelDB's strength, which is to do large numbers of writes to a database that's 5 times larger than RAM. I said, okay, I'll try that. I got 8 gigs of RAM on this laptop. I'll write to a database that's 40 gigabytes in size and see what happens. And what happens? Lightning database is more than twice as fast as LevelDB. So I'm going to do this to that Google guy multiple times. Okay, so instead of just micro benchmarks, see some applications. First of all, Memcache Test results. So this is the output from the program called Memcache Test. It shows you the minimum speed, the maximum speed, as well as the 90th percentile, 95th, and 99th percentile, and the average. So higher bars are worse, are slower. So this is time for each operation. On the left, you have read operations for a single client thread, and on the right, it's write operations for a single client thread. You see that BerkeleyDB is much slower than anything else. And you see that Lightning Database and Memcache D are fairly close in speed. Memcache D is a little bit faster on writes. Then this is the same test using 4 client threads. So now we're getting into multi-threaded access. And what you find here is that although Memcache D actually has a much faster minimum response time, on average it's slower. And it also has a much slower worst case response time. So that's something else for you to keep in mind. When people say, oh, main memory databases are the fastest you can possibly get, that's not true. Here's results bulk loading a database in SlapD using BerkeleyDB and Lightning Database. And again, the bars are the amount of time taken to perform the bulk load. There's 3 sets of numbers. The first one is for a single-threaded load. The second one is for a double-threaded load where we have parsing in a separate thread from database operation. And the third number is for multi-threaded indexing, where we perform all the attribute indexing in a separate thread. And it turns out that our multi-threaded indexing code is very bad. We spend most of our time in lock overhead there. But ultimately, the Lightning code is about twice as fast as Berkeley, just for bulk loads. This is for a database with 5 million entries. The guys at Zimbra just ran another test on their own customer data, and they're showing 3 or 4 times speed difference. So it depends on the format of the data as well as the types of indexing you're using. But you'll always see at least a 2x speed increase. This shows you the size of the SlapD process and the size of the database on disk. So on the left column is the size of the SlapD process after we've performed a search that reads the entire database into memory. So here we see that BerkeleyDB is over 4 times larger than Lightning Database. And on the right side, the database size on disk, we see that Berkeley is about 80% larger on disk. So we do much more efficient data packing in Lightning Database. This chart shows the amount of time it takes to perform a single search that scans the entire database. The leftmost column shows the very first search from a cold start with nothing in cache. So the blue column shows BerkeleyDB takes over 4 minutes to read the entire 5 million entry database, and this is the time it takes to populate its cache. And you can see that MDB, Lightning Database, took about 13 seconds. The second column, second set of numbers, is the exact same search repeated now that the cache is loaded. So in that case, Berkeley takes about 16 seconds, and Lightning Database took about 10 seconds. Then the remaining sets of numbers show the exact same search being repeated, but multiple times concurrently. So with 2 clients concurrently, 4 clients concurrently, 8 and 16. This is being done on a machine that has 16 CPU cores. So ideally, you should be able to get 16 searches running simultaneously. And what you see is that with Lightning Database, the search time is constant. It's about 10 seconds for every case. But with Berkeley DB, the search time gets asymptotic because, again, it's got a lot of lock overhead. And as the lock overhead gets much worse as you perform locks across multiple CPU sockets. So the difference between 2 threads and 4 threads isn't so bad because it's a quad-core processor. So all 4 of those threads are probably running on the same CPU socket. But when you start crossing socket boundaries, then the performance really goes in the tank. So this shows the aggregate search throughput for a SlamD workload, where we've got hundreds of client threads beating on the server as fast as possible. The leftmost column is with Berkeley DB. The next column is Lightning Database. The other 2 columns are for 2 other directory servers. So even before we had Lightning Database, OpenLDAP with Berkeley DB was the fastest in the world. It's been the fastest in the world since 2005. But now we're about twice as fast again. And the other guys haven't really changed. So that is actually my last slide for you. So if you have any questions. Yeah.
Do you have issues because of the switching between the 2 Btrees in this case?
The switching is atomic. I mean, it's almost invisible.
So you can't have 2 sets of readers, one on the old Btree, several others on the new.
Yes.
The writer who says, oops, I can't write.
No, at the beginning of a transaction, each transaction takes a snapshot of the current node. Once it's taken that snapshot, it releases the original. So there is no blocking. Yeah. Yeah.
So you said that you don't store every version of the modification, but would it make sense to have an option to have this feature? Because sometimes it would be very interesting to go back in the history, for example, 1,000 transactions before this one.
Yeah, I agree with you. Sometimes it's interesting, but that's not a use case that we want to use. It's not for OpenLDAP anyway. Yeah.
By the way, it seems to be, I just checked the web page. It's very linked to OpenLDAP. It seems to be something, I mean, we could use it for anything else. We present it in the slides, but why do you emphasize the fact that it's linked to OpenLDAP?
Well, it was originally developed inside the OpenLDAP project, and our goal was simply to replace Berkeley DB inside OpenLDAP slapd. But what we found after a lot of testing was that we could actually apply this in other applications too. So it's just a matter of what we originally set out to do is different from where we are today. Yeah.
Just to make sure I understand, so the writes are not sequential in your case, they are not automatically, right? Because you come back to rewrite the same pages. So it's not an atom-only B tree.
It's not a pure add-only B tree, no.
So you come back fairly often, don't you? Because
Yeah, we come back every other transaction, yeah.
Not only on the roots, because you also for the list, you will delete them, so I suppose you will override the same page.
And any page that hasn't been used in the past 2 transactions is available for reuse. Yeah. Yeah.
Can the database be opened in a multi-process context, or is it only multi-thread?
No, it's multiprocess. Yeah. Yeah. Oh, yeah. Is there what? Yeah, there's Python, there's Ruby, there's Lua, there's Erlang. So, we will work on a Java one. Yeah. Not yet, but it will be. Yeah.
Any plan for clusterization or verification on several nodes?
Not inside this library, but that's one of the reasons why we're looking at, for example, we're looking at RIAC and we're looking at Hyperdex. Both of those are NoSQL databases that do support replication. So our goal will be to use Lightning Database as a backing store for them and use their replication engine. Yeah. Yeah.
In case of multiple processes, how many do you use? How many writers do you use?
There's only one writer ever. Yeah, as soon as we start talking about multiple concurrent writers, then you get into the issue of having deadlocks, and that slows everything down. What we found, even in testing with BerkeleyDB, is if we put a global lock around BerkeleyDB, our write throughput improved. Yeah. So there really isn't a lot of advantage to allowing multiple concurrent writes. Yeah.
Yeah, but think about the multi-value storage. You're just copying all the values that you have associated with a key each time you add a new value.
Yes.
Would it be better to use a set B-tree to store those multi-values? Because then you avoid some page duplications.
We can do that. We support the multi-keys subtrees. And we do that in our index tables in OpenLDAP. But there's a little bit of overhead to set up the subtree. There's a 48-byte header for that. So if you're doing that for millions of entries, that starts to eat into your space. Yeah. Yeah. It's one writer for the environment.
Okay. So we cannot have 2 databases, 2 writers.
You can have 2 separate environments if you want. But if you're using multiple databases within one environment, yeah, then only one writer. We actually have an experimental patch to allow writes to multiple databases in the same environment. That probably won't be released for a few months. Yeah. Yeah. Oh, yeah?
Is it possible when you play reggae music?
All right. No further questions? Thank you for coming.